Hello again, my wonderful students. We're ready to start a new chapter. That's chapter 4. We're doing 4-1 functions, part 1. I forgot to put part 1 up there. Lots of vocab to start off. This first section of chapter 4 is usually a pretty difficult one for my kids. But then they look back on it when the chapter's over and they say, oh, that wasn't that hard. Anyway, the first definition. You're going to define a function. A function is a special relation that assigns each member of one set, and that set is usually, we call it the x values. You could also call it the domain. It assigns one member of the domain to exactly one element of another set, and those are usually the y values, and sometimes we call those, actually all the time we call that the range. So for instance, you've been doing this since Algebra 1. Don't let that definition confuse you. Let's assign 0 to 0. 1 gets assigned to 4, and 2 gets assigned, 1 gets assigned to 1, and 2 gets assigned to 4. So we could write that as a set of ordered pairs, right? That's 0, 0. 1 was assigned to 1, and 2 was assigned to 4. The reason they were assigned to those numbers was because this was the function f of x equals x squared. For every input, you square, and you get the output. That's a function. Each x is assigned to one and only one y. Some examples, any equation that looks like this. Anything that looks like y equals mx plus b, it's a function. It's a line. Each x has one y. Or if you have y equals ax squared plus bx plus c, that's a quadratic function. Looks like a parabola. Again, each x only has one y. Now, some of the y's have more than one x, but we'll worry about that later. And finally, this is a function. If you plug in the name Williams for your input, you get November 30th for the output. I'll leave it up to you to try and figure out what I'm trying to say there. And just so you know, I like brownies on my birthday. Okay, so those were examples of functions. Now let's talk about a non-example of a function. Here's a non-example. X squared plus y squared equals 25. Does anybody know what that looks like if you graph it? It's actually a circle with radius 5. So go up 5, left 5, down 5. Has a center at 0, 0, and whoop, there's our circle. That's not a function because take for instance this x value right here. Let's call it, 2. It would get assigned to this y value, and that would be, let's see, 2 squared is 4, take away, that'd be the square root of 21. And it'd be assigned to this x value, which is negative square root of 21. So that x is a cheater. He's dating two different y's. Well, that means we don't have a function. That's a non-example. There are other ways to determine if you have a function or not. The most common way is the vertical line test. Vertical line test. So let's say, for instance, you have a sideways parabola. Function, not a function. Well, if you can draw any vertical line such that it passes through twice, 1, 2. That means it's not a function. Why is that? Because that x value has more than one y value. And we said that each x can only have one and only one y. What if you had a graph that looked like this? Looks kind of like teeth. Is that a function? For every vertical line you draw, does it only pass one time? Well, it sure does it. There's not one vertical line you can draw such that it passes more than once. So we say that is a function. What about this bad boy? Ready? Here we go. He's going to be cool. Boom, boom, whoop. Big circle. Boom, whoop. And below that circle, put a big old dot. So the function actually has a point of discontinuity at that big circle, but it's valid at this dot. Is this a function? Let's see here. Draw a line here, only touches once. We're okay. Draw a line here, only touches once. We're okay. Draw a line here, and wait a minute. Does it touch twice or not? Oh, it doesn't touch at this circle, does it? It touches down here at the dot, so it only touches once, which means yes, this is a function. That one's a little tricky. It gets my students about every year. Okay, some more definitions. Now we're going to talk about a relation. Now, every function is a relation, but not every relation is a function. Did you hear what I just said? Every function is a relation, but not every relation is a function. A relation is a set of ordered pairs, I should say of. A set of ordered pairs. Any set of ordered pairs. It can be written, as part of an equation. Or it can be a set of ordered pairs from a graph. That is a relation. Anything. Any set of ordered pairs. It can be a function or it can be not a function. Here's an example. Y equals plus or minus the square root of x. If you graph that, do you know what it looks like? It looks like kind of like a sideways parabola. There's the positive half and there's the negative half. And that one's actually not a function, but it is a relation because it's a set of ordered pairs. You could make a table. Okay, a little bit more vocab before we get too crazy. Domain. We've talked about domain a lot so far in this class. You all are probably tired of hearing domain, but it's not going away. Alright, it's a set of inputs, or it's easier to think of them as the set of x values that you're allowed to plug into a function, or we say over which a function is defined. Alright, and the domain is always left and right. The right endpoint is called the horizontal. I can't spell horizontal. Horizontal max. And the left endpoint is called the horizontal minimum. So the domain is how far the function goes left and right. The range is the set of outputs, or the set of y values that are included in a function that result when you plug in all of your x values. And here we have a vertical max and a vertical min, and the range has to do with going up and down. Alright, so let's use what we've learned and apply it to a bunch of different examples. Number 1, part A. We're going to go all the way to part H. List the domain, the range, the zeros, and sketch the graph. Try your best to do it without a graphing calculator, but if you need to use a graphing calculator, that's okay. So this first function is just a linear function. It's y equals mx plus b. Let's graph it first. Starts at 3, and it goes up to right 1. Do your best to make these look nice and neat, guys. Don't give me slop. Make them look good. So it's just a line. Alright, that's definitely a function. What's the domain? What values of x are you allowed to plug in? Is there any x that you're not allowed to plug in? No, it can be any x. So the domain is all x's such that it's all real numbers. You can plug in any x you want. Think of it as it goes, this arrow will go forever right and forever left. It will never stop going right and never stop going left. The range, same thing. It never stops going up. It never stops going down. So the range is all f of x's or y's such that it also includes all real numbers. And finally, the third part, find the zeros. And when you find the zeros, it's real easy. Just set your function equal to 0 and solve it. Works the same every time. And so the 0 is x equals negative 3 over 2, or about negative 1.5. And if you'll notice, it crosses right here at about negative 1.5. That's the 0. Alright, let's kick it up a notch, shall we? Part B. So here's what I've given you. F of x equals 1 minus x over 7. This one's just a little saucier. Okay, so here's the question. Is the domain all reals, or are there any restrictions? So for the domain, I want you to ask yourself, what are the restrictions? Are there any values of x that you're not allowed to plug in? Well, remember, the denominator is never allowed to equal what? The denominator is never allowed to equal 0. It can't equal 0. Well, that means that x cannot be what, guys? X can't be 7, unless you're Chuck Norris. So our domain is we can plug in anything we want, all real numbers. So it's all reals except restricted. X is not allowed to be 7. So what that actually means then on the graph, since x cannot be 7, is that over here at 7, there's a chung, 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 chung. We call that an asymptote. There's a vertical asymptote that but the graph will not pass through because x is not allowed to be that number. So go ahead and draw that in. Now it might help us to sketch this graph to make a little table. This table is going to help you a lot in this section to make a little table. And you can also get these tables from your calculator. Just graph them and look at the table. Put your restricted value in the middle. Now 7 gives us no solution. We can't do it. We already tried. Go around the 7 though. If you plug in 8, plug it in right here for x, you get positive 1. So plot that point. If you plug in 9 to the original function, 1 over 9 minus 7 is 1/2. So 9 gives you 1/2. Plug in 6, you get negative 1. 5 gives you negative 1/2. So kind of plot those numbers. 6 negative 1, 5 negative 1. You can kind of see what this is going to do. It's going to do one of these. It's going to go and it's actually a graph that has 2 pieces. And it chases the asymptote but never quite touches it. It gets closer and closer and closer but never actually touches it. Alright, let's go ahead and try to find the zeros. Now remember, to find zeros, you set your function equal to 0. So 0 equals 1 minus x minus 7. Now some of you might already be asking, Mr. Williams, I thought that's where it crossed the x-axis. And look at your graph. It never crosses the x-axis. And you know why? Check this out. Solve this. Times by x minus 7. Times by x minus 7. You get 0 equals 1. Well, last time I checked, guys, 0 cannot equal 1. This can never happen. 1 divided by nothing will ever give you 0. It's not going to happen. So for the zeros here, there are none. It will never cross the x-axis. Now you should be able to finally tell me the range. All f of x's, all y's. This function goes up forever, it goes up forever, and it goes down forever. But what y value does it never hit? Well, since it never has a 0, it never crosses the x-axis. So we're going to say it's all real numbers except f of x, just like the domain had a restriction, the range has a restriction. It can never be 0. That was saucy. Absolutely. Okay, that's going to come up a couple more times. Rewind that video if you need to and take a look at that one again, because that was an important problem. Okay, looking at this next one, here we go. We got f of x is the square root of 5 minus x. Now, whenever you take the square root of something, that has to be what kind of number? Positive or negative? You can't take the square root of negatives. It's complex. So that number has to be positive. Well, if we know that, then we know it's got to be greater than or equal to 0. Well, that means x, when you solve this, just add x to both sides. X has to be less than or equal to 5. You know what that is, guys? That's your domain. X must be less than or equal to 5. Otherwise, you get crazy, stupid results. So domain is, that should say all x's, such that x is less than or equal to 5. And check that out. Let's make a table. Watch this, okay? Watch this. Put 5 right here, okay? Plug in 5 to your function. 5 minus 5 is 0. Square root of 0 is 0. Plug in 6. 6 minus... I'm sorry. Oh, I did that wrong. Erase the 6. Remember, we said the domain has to be smaller than 5. So let's plug in 4. 5 minus 4. Sorry, 5 minus 4 is 1. Square root of 1 is 1. So we can plot this. 5, 0, 4, 1. Plug in 3. You get the square root of 2, which is like, about 1.4-ish. But if you plug in 6, what are you going to get? If you plug in 6, you're going to get the square root of negative 1. Error. That's not real. You can't graph it. Don't know what it looks like, do you? Okay, cool. So, that's our domain. Only numbers less than 5 are you allowed to plug in. You can also go ahead and kind of sketch this curve if you want. Looks like a half of a parabola. That's what it is. It's half a parabola, but it's turned sideways. And it's kind of going backwards. You tell me, now could you tell me the range? All f of x's such that what? Let's see here. Beep, 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 beep. Stop. The range stops. what y value does it stop at? It's going to get bigger and bigger and bigger. Look at this right here. Where did the range start? The domain started at 5. That's the x column. Where did the range start? It started at 0, and what are these numbers doing? They're getting bigger. That's right. So the domain is all f of x's greater than or equal to 0, because it's only above the x-axis. Only above the x-axis. It goes up forever. Sweet. All right, and finally, let's find the zeros. So, and you can probably tell this just from looking at the graph. Where does it cross the x-axis? It crosses at 5. But let's prove it. Take your function, set it to 0, and solve. Let's square both sides. So 0 is equal to 5 minus x. So x is equal to 5. There's the 0 that we said. Cha-ching. Wasn't that awesome? That's awesome. Love this stuff. This is hard for you all because every problem is a little bit different, and you really have to understand domain and range to be able to do this stuff. Okay, next one. This one gets even saucier. So, same thing, we got a square root function. So again, this bad boy right here, whatever's inside the radical, it's called the radicand if you're a nerd, this must be positive. Must be positive. So take that hunk of junk and set it greater than or equal to 0. Now let's solve that. Okay, actually you can just set it equal to 0 when you're solving it. So that means x squared added to both sides is equal to 1. That means x could be plus or minus 1. And in this kind of problem, those are known as boundaries. Boundaries. Okay? Check this out. Boom. 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 Make a table. Put in your first boundary, -1. Plug it in for x. Boom. What's -1 squared? That's 1. What's 1 minus 1? 0. You get 0. So -1 gives us 0. Plot it on the graph. Put it on a graph. Alright, plug in +1 for x. Okay, 1 minus 1 squared, boom, it's 0. You get 1 again. What's in between -1 and 1? What am I missing? I'm missing 0. Let's plug that in. What's 1 minus 0 squared? 1 minus 0 squared, that's 1. Square root of 1 is 1. Boom. Can you tell what this is going to look like yet? This is going to take on a half circle. That's all it is. Isn't that a cute little graph? Say, man, that's a cute little graph. Yeah, that's it, guys. Think about it like this. Okay? Put in -2 right here. Or put in +2. I don't care. Pick +2. What's 1 minus 2 squared? 1 minus 2 squared gives you the square root of -3. That's not real. You can't do it. You can't graph it. So this is all your graph looks like is right here. This is a little half circle. Isn't it cute? Alright, so let's do domain. The domain are all the x values you're allowed to plug in. Now you can look at the graph. It goes from -1 to 1. Or look at your table. From -1 to 1. So let's do that. -1 less than or equal to x less than or equal to 1. That's your domain. What about your range? F of x such that, look at the graph or look at the table, it doesn't matter. Where does the y value start on this graph? What's the first y value you see here? Well, this is the point 1, 0, up to what? Up to 1. Those are the only y values you're allowed to get. So we would put, okay, it's 0 less than or equal to f of x less than or equal to 1. That's your range. And you can also get that right here from the table. Look, it ranges from 0 to 1 and 1 back to 0. Never higher, never lower. And finally, the zeros, where do they cross? Well, we already found those. It's +1 or -1. Those are the zeros. Alright, awesome. Later on this year, you're going to have a memorization quiz where I ask you to give me the graphs of all the parent functions. And that's one of the parent functions right there that you just saw. Okay, moving right along. Here's one that's very similar. Again, this must be positive inside here. Okay, so set it equal to 0, and we're going to get our boundaries again. Add x squared to both sides. So x is plus or minus 3. That means your domain is going to go from negative 3 to 3. Watch, I guarantee you. Same thing, to find the zeros, you essentially do what we just did, but set the whole thing equal to 0. Square both sides. You get exactly what we just had. So x equals plus or minus 3. Those are your zeros. Let's go ahead and put those down here. And if you want, you can go ahead and put those points on the graph. Plus or minus positive 3 and negative 3. Cha-ching. Check it out. Alright. This is going to be another half circle doodad. Watch, okay? Let's do an input-output table. I'm going to do a sideways table this time, just to mix it up. So input the x's, output the f of x's. Start with your first x, negative 3. Plug it in, plug it in. Alright, when you plug it in for x, negative 3 squared is 9. 9 minus 9, 0. Plug in negative 2. Let's just work our way across from the left. Negative 2 squared is 4. 9 minus 4, 5. So we get the square root of 5. It's about 2.2-ish. 2.2, yeah, something like that. Let's plug in negative 1. Negative 1. Let's see here. Negative 1 squared is 1. 9 minus 1 is 8. So we get the square root of 8. It's almost 3. So let's plug in 0. See what you get. Remember, we're just doing all the numbers in our window. Or all the numbers in our range, sorry. 9 minus 0 squared, that's 9. Square root of 9, 3. Well, that's an easy point to graph. So I had negative 2 square root of 5. That's about 2.2. Negative 1 squared root of 8. That's about 2.7, 2.8. Boom. You see what's happening here? It's half of a circle again. Watch. Watch. I bet it's going to do something like that. Let's try 1. 1 is again going to give you square root of 8. 2, square root of 5. And 3, 0. And anything outside of that window is going to give you an undefined value. So your domain, all x's, from negative 3 to 3. That's all you're allowed to plug in. Range? Look at these numbers down here. The smallest you see is 0. The biggest you see is 3. Look at the graph. Up to down. It starts at 0 and goes up to 3. That's your range. Sweet. So 0 less than or equal to f of x less than or equal to 3. And we already did the zeros on that one. Sweet. That was a good one. I like that one a lot. Okay, just got a couple left. Here we go. This one's even saucier. Alright. So this time I have 1 over the square root of x minus 4. 1 over the square root of x minus 4. So again, this guy right here, he must be positive. But also the denominator cannot be 0. You need to remember that too. Well, what's that mean? That means x is not allowed to be what numbers, guys? You should be able to tell that just by looking at it. X can't be positive 2 or negative 2. Those are points of discontinuity. And what did I tell you that happens there? Remember? Chung, 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 chung. Go to 2 and draw in the asymptote. Go to negative 2, draw in the asymptote. Chung, 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 chung. Those should really be dashed lines. But alright, so here's the question. What values of x are you allowed to plug in? Let me write that. What values of x can I plug in and get a real result? So I don't want anything that has an I in it. I don't want anything that has an I in it. Well, let's just play around with a couple numbers. Okay, try negative 2. Well, negative 2 is going to give us 0 in the denominator. But wait a minute. 1 divided by 0? No solution. Can't do it. World falls apart. Try positive 2. Same thing. No solution. Try positive 1. Okay. That gives me 1 over. 1 squared is 1. I'm plugging it in right here. 1 squared is 1. 1 minus 4 is 3. So I get 1 divided by the square root of negative 3. Uh-oh, that's not real. Can't do it. So if I can't plug numbers in between negative 2 and 2, maybe I can plug in numbers outside of negative 2 and 2. Try 3. You get 1 over the square root of 5. Now that's not a very pretty number, but is it real? Yeah, it's a decimal. It's a decimal. Guys, on your calculators, or if you make a table, you're going to get something that kind of looks like this. It's a two-part function, or a two-part graph. That looks kind of like that. It's got two pieces, and it chases those asymptotes. All right, so what's our domain here? We're allowed to plug in any x's over here that are smaller than what? Smaller to the left of -2, less than -2, or bigger over here, bigger than +2. You got to go outside those numbers. And range, f of x, okay? Where's the range begin? Well, remember, the range is up and down. So it goes down, 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 down. It keeps going forever to the side. Where does it never hit? It never hits the x-axis. So it looks like the range starts at y equals 0. Think about that. This is the line y equals 0. But it goes above it. It never equals it. So it's just greater than 0. And for 0, since it never touches the x-axis, there's none. I mean, ask yourself this. Set the function equal to 0. When will that be true, folks? 1 divided by what equals 0? 1 divided by what equals 0? If you can figure that out, you'd be the smartest person alive. Because it's impossible. You can never divide 1 by anything and get 0 for an answer. Alright, let's try this one. Okay, so this one's similar. Now, you can factor the bottom to t plus 6 and t minus 4. So what is t not allowed to be? Our domain cannot include -6 and +4. So go to 4 and go chung, 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 chung. Those are the points of discontinuity. Go to -6. Chung, 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 chung. Asymptotes. Can't cross those. Our domain then, okay, x can be anything. It can be all reals except what? Oh, by the way, that should not be x. What should it be? I'm glad you caught me. That should be t. Except t cannot be -6 and 4, because if you plug in those, the world falls apart. Alright, the range I'm not going to worry about on this one because you kind of need calculus, and I'm not going to mess with that. Alright, the 0, set your function equal to 0. And this is the same thing as the last one. Okay? 1 divided by what? 1 divided by what gives you 0? Nothing. Nothing, so there are no zeros. None. Alright, if you sketch this curve, this is a crazy curve. It kind of looks like this. It's got one piece that does this, chases the x-axis and chases the asymptote. Another piece over here that chases the x-axis and chases the asymptote. And then you got kind of a downwards parabola looking thing in the middle. That looks like that. Pretty crazy. You can make a table to find those values, or you can just plug that into your calculator and get a table from your calculator. Pretty cool. Okay, last one I'm going to do in this video, and this is an important one. Very important here. Actually, I'm going to do 2 more. I'm sorry, I lied to you. These are absolute value functions. So, graph the absolute value of x minus 3. Now, an absolute value functions always look like v's. Always look like v's. You should remember that from Algebra 2. Okay, this one is the absolute value of x minus 3. Well, if you plug in 3, you get 0. If you plug in 3, think about that. If you plug in 3, you get 0. Do you believe me? Plug in 4, you get 1. Plug in -4. Oh, what do you get? No, I don't want to plug in -4. I want to plug in 2. I don't know what I'm thinking here. 2 gives you -1, but the absolute value is +1. So you can kind of see it taking this V shape. Do you see it? Now the domain is what? What can you plug in? Well, you can plug in anything you want for x. Plus, the graph goes forever to the left and forever to the right. The green arrow, it's never discontinuous. It always keeps going. The range, though, has a restriction. Okay, the range starts at 0 and gets bigger. See that? It starts at y equals 0 and they go up. So the range is f of x is greater than or equal to 0. And finally for zeros, well, set your function equal to 0. Okay, or just look at the picture. It crosses at 3. That's the 0. Sweet. Awesome. Okay, I promise, this is the last example for this video. Okay, this one is the absolute value of x with the minus 3 on the outside. So it's a lot like the last one. But now that the minus 3 is on the outside, instead of shifting the graph left and right, it's actually going to shift the graph down. Think about this. If you plug in, say, 0, you get negative 3. So 0, negative 3. It's almost like the vertex on a parabola, but not quite. Plug in 1, you get negative 2. Negative 1, you also get negative 2. Plug in 2. Plot those points. Plug in 2, you get negative 1. Negative 2, you also get negative 1. So you can really see it taking on this V shape, can't you? 3, you get 0. Negative 3, you get 0. All I'm doing is plugging these into the function. Boom. Now that's handy because now we know the zeros of the function. The zeros are plus and minus 3. The domain, usually on absolute value graphs, the domain is all reals, and it is in this case as well. Goes forever left. But the range is restricted. What's the range restricted to? Well, it goes down, 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 down. Stop! Where does it stop? Down, 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 down. Stop! Where does it stop? It stops at negative 3 for the y value. So the range is, okay, f of x can be anything bigger than or equal to, can't write that. F of x can be anything bigger than or equal to negative 3. Look at your table. Does that confirm your table? Okay, negative 3 is as small as the y's get, but then they get bigger and they get bigger. Guys, domain and range is so simple. If you just think about it, it's what x values are part of your graph and what y values are part of your graph. And that's it. That's all domain and range is. Alright, that's all I got for video 1. Check back for part 2 here in just a little while. I will catch you later. See you later. I'm out.